Hey, what's happening, guys? In this video, Peter Talsanis and I carry on working on that rate limit function we were working on last week, but you don't need to have watched that video to work with this video. The link to the video and the code that we ended off on are in the description below. Essentially, the problem with that code was that it wasn't thread safe. And in this video, we tackle making that code thread safe. So let's get started.
On Clojure.
There's a slightly nuanced problem with the code that we've written, and it would be somewhat difficult to demonstrate at the REPL, but I can tell you why I am aware, or basically I would tell you how you would become aware of the existence of this problem, which is here. Whenever you're dealing with atoms, be aware that usually one of the main motivations for having an atom in the first place is in order to have atomicity, right? That's where the word atom comes from, the name atom. Atomicity. In other words, you want to be able to do certain kinds of things in a way that is thread safe. Where our radar should be kind of having, a sense that something might be weird here is that we're dealing with we're using atom for our state, but we're doing a deref over here. In other words, we're asking what is the current value of this atom, and we're doing a reset over here where reset changes the value of something without concern for what its current value is. And in fact, if you look at the docstring for reset, this is what it explains. Sets the value of atom to new val without regard for the current value. So this is the important thing, without regard for the current value. That's an unusual thing to do with an atom. And what I would generally recommend is, especially for folks who are new to atoms and Clojure, just have your radar out for derefs and for resets, because they are both doing something that might match your particular intention, but they are also both often a source of subtle multi-threaded problems, because it appears when you're doing a simple example in the REPL that everything seems fine, but actually there's a subtle multi-threading thing that can go on when multi-threading that could cause issues. And basically it's this. We're derefing a value over here at a point in time. We're then making a decision about what to do with that deref value, right? So last executed is a value at a point in time. Then this is calculated, a calculation made with that point in time value, which is determining which branch we're on, which is then going to calculate this result. And then we're going to change the state based on some information that we now have. But we actually got into this branch because of a point in time check over here. It could happen that two threads are calling this wrapper. Remember, this is the wrapper that we're returning to our consumers. It could happen that our consumer is calling this function wrapper from two different threads simultaneously, and two of those threads do the deref at last executed. Two of those threads calculate the elapsed time. Two of those threads calculate that the elapsed time is sufficient for a re-execution. Two of those threads calculate the result, executing F, and two of those threads do a reset to change the last executed time. It might happen that two printlns are going to happen, and two calls to the underlying function are actually taking place. And what we're actually trying to do as part of our API, which goes all the way back to the wrapping once, is that we want to make sure that this is sort of a thread-safe promise that F is only going to get called once. The difference is in the wrap once in a while, we want to make sure that F is only being called once in every msex period. But we don't want to have it be that if you call F from 3 or 4 threads all at once, that it might happen that it actually executes 4 times or 3 times or twice in a short period of time.
So we basically have a condition that can pass multiple times in multiple threads, and that's what we don't want. We want that last
exactly.
Yeah.
This is an interesting problem. How do we make our code or our implementation here atomic in the way that we would like for the API that we're hoping to provide to the consumer? Any ideas?
I think you would need to block the thread from at that point, and I actually don't know how to do that in Clojure.
You would have a few options here. One way would be using something like a lock. So basically what you would have is when you're calling into this function, you would effectively be saying, look, while I'm running this code, I'm going to lock some shared object so that no other thread is running this same code at the same time. That would be one way of going. And that would be, let's say, not an unusual approach in something like Java and so on, and certainly would do the trick over here. Let's try and do it without a lock, because one thing that is nice about Clojure atoms and so on is that, generally speaking, the conceptual idea behind this atom thing in Clojure is that you're doing sort of optimistic state modification that is not dependent on locks, but you're going to make it instead more dependent on things like this compare and set. In other words, you're going to acknowledge that the common case is that another thread is not actually in contention right now, and that it's not trying to stomp on your work at the same time in the common case. You just want to verify at some point along the way that somebody else hasn't attempted to do something on another thread, and you just want to verify that as a piece of safety. But you don't want to incur the cost of a locking mechanism when you expect the common case is actually there's not going to be a lot of contention on this thing. What we want to avoid is this notion of dereffing over here and then doing an unconditional reset over here. We would probably like to try and lean somehow on the swap. In other words, we want to do some sort of a conditional change. Just to remind, if we look at the docstring over here for reset, you'll see over here the docstring is it's just going to change the value without regard for the current value. And in comparison, if we look at the docstring for swap, you will see over here that it atomically swaps the value of atom to be this. I would note one thing for folks, if they're interested in doing this in their own time, is to look at the source code of swap. It's quite an interesting piece of Clojure core code to look at. If you actually look at the Java implementation, I can't access that right now, but if you look at the actual Java implementation of swap under the covers, which would need you to open up the clojure.lang.iatem Java code, you'll see that swap is actually a very, very simple thing. Basically, all it's doing is it's some sort of a loop where it's getting the current value. So I'll show you over here. It's something like this. Then new val, apply f of args, and then it's doing something like if compare and set val to new val, then we're going to return the new val or whatever, otherwise we're going to recur. Again, I don't want to go into this in too much detail, but I want to note that this is it's interesting to understand that the Clojure atom is actually a very simple thing. There's not much to it. And it's basically just a wrapper for Java's own, util.concurrent whatever atom stuff. And it's very, very simple. And basically under the covers, this is all that an atom is. When you're trying to do an atomic swap, basically it's just checking the current, it's dereffing to get the current value. It's calculating the application of your function, then it's trying to check, is the value still what it was at the time of the deref? In other words, is the value still current val? If yes, put in your new val atomically, which is using the Java util concurrent underneath, and then return whatever. And if it doesn't, if the current value is not what we derefed a moment ago before calculating your function f, then just recur this whole loop. In other words, keep trying. And in fact, if you read the docstring for swap over here, it says over here, note that f may be called multiple times. The reason for that is because of this loop. So the way that Clojure's swap is implemented is it basically optimistically executes f, and if it turns out that there's been a concurrency violation and somebody else has actually changed the value out from under that call to f, it will just recur, which means f might run multiple times, which is one of the reasons, by the way, that generally speaking, the advice is to try and make the function in a swap call as cheap as possible. Now, don't put a lot of expansive logic in f because f may be called multiple times. And it's also why there shouldn't be side effects, which should be in the docstring, I believe, as well. Should be free of side effects because f might be called multiple times. So you don't want it to be too expansive and you don't want it to be having side effects. So we want to use swap somehow. What are our options over here? Basically, the idea is we want to be able to make sure that this whole result is only ever being called one time, which means that the thing that we need somehow there to be an atomic ability to do some sort of a calculation against this state and actually update it when the conditions are correct. So that sounds complicated, but let's actually just fiddle with this a little bit and see what this might look like. So let's do a swap over here. Let's do a swap at against last executed. So again, if you do the docstring for this, it's going to go
we have to last executed with the unscore.
Exactly. Does that make, yeah. I see, thank you. Does that make sense so far? So we've got the general shell structure over here, which is we're going to do some sort of an operation, an atomic operation against last executed underscore, against the container, against the atom itself. The argument that we're going to have inside of the function is actually what the current state is. So that's what the last executed is. And there is logic in here that ultimately needs to return the new value for last executed. So what we can do is maybe move some of this value, some of this logic over here. Let's just take this out. All right. So we've moved the calculation of the elapsed time from something that was happening after a deref, and we're now instead moving it into a function which the swap API is telling us, is guaranteeing to us, is going to be executed atomically. We're going to calculate the elapsed time in here, and we're going to have something like this. When elapsed, so this is, okay, so we're focusing here on the general skeleton of what we're working with. So we're doing a swap against the atom. This is the function here. We're providing a function which is going to be called by the swap API. The swap API tells us that the argument is going to be the current value of last executed, right? So this thing derefed at a point in time. So we know that we're at this point, and we have current last executed. Then we can calculate the elapsed, like we did before, which is straightforward. All right, so we have the elapsed calculation over here, and we can do a conditional, as we did before, about whether we have actually exceeded the minimum period or whether we have not. So let's say exceeded, which implies that we want to now execute, and not exceeded, which implies don't execute. So effectively, we've moved the calculation of whether we're elapsed or not. We've moved it into a function which has an atomic view of the current state in an attempt to eventually make this implementation thread safe. In particular, to make sure that the implementation never calls f more than once for multiple threads. At this point, we know whether we have exceeded the period or not, and we're inside the body of a function which is executed atomically. The idea is the return value over here should be new state when exceeded minimum period, and new state when not exceeded min period. So that's our responsibility. This is, again, if you look at the docstring for swap, right, it's telling us what it provides, and it tells us what we need to provide. So it says that the new value of the atom is going to be applying f whatever over here, which means that our function, which is this f over here, this is the swap function, our f has the responsibility of returning the new state that should be in place. And since we have this condition over here about we care about the difference between whether we're elapsed or not elapsed, it's our responsibility to return some kind of new state when we have exceeded the minimum period and some kind of new state when we have not exceeded the minimum period.
When we have exceeded the minimum period, so we've waited a long enough time, we want the last executed time to be now, but we need to execute also.
Yep. So we'll do something like this. So I'll keep this in here for now. Say M6 period did M6 period call F, and we'll say did not exceed M6 period no up. Okay, and in this case it's relatively easy. We know that from the API that we're promising, we're just going to return nil. And in this case, when we actually want to return the new thing, we're going to first calculate the result, which we've got over here, and then we're going to do something like that. But there's a problem here because, again, according to the docstring of swap, what our function f needs to actually do is return the new state. In other words, this is the API that our wrapper is supposed to provide, as is this. This is sort of the API that we want to provide to the consumers of our wrapper. What the function over here actually requires is the new state. In other words, what it requires over here is actually new state. So we do new state when elapsed. We do new state when not elapsed. So the issue over here is our first responsibility is to make sure that we're returning what the swap API requires, which means that we need to actually put this in form of new state. In other words, what we should have over here is now, and what we should have over here is actually current. I'll show you what I mean. What's this thing called? Last executed. So what the swap API actually wants us to do is, in this branch, the new state, in other words, the new last executed, should actually be now. And in this branch, in other words, when we failed this conditional, we should actually leave the last executed the same. We don't want to change it. Something like that.
Yeah.
So another way of looking at it is we could maybe, just to scratch that out for a second, we could say this could be our swap function, where we're swapping against last executed, and we're calculating the elapsed time. If the elapsed time is bigger than the M6 period, we're changing the last executed to be now, and if it didn't elapse, then we leave it unchanged. In fact, what we want to do is move all of this stuff anyway out of the body of the swap function, because as we pointed out, the docstring of swap mentions that f may be called multiple times, which means this whole body over here can be called multiple times. And the whole point of doing this thing, this body atomically, is we don't want the apply f to potentially be called multiple times. The actual solution in this case is to take this whole result thing out of the atom entirely, or at least that would be my inclination right now. We'll see how this goes. I'm just cutting this out right now, and we're trying to look over here. All right, so what do we have? We have this wrapper. We enter the call against the wrapper. We check what the current time is. We save it over there. We now try to do an atomic swap against the last executed, which is our state. We're going to calculate the elapsed. If a sufficient amount of time is elapsed, we're going to set the state or the last executed state to now. Otherwise, we're going to leave it at last executed. This whole thing is going to return, which we can check in the docstring, returns the value that was swapped in. In other words, it's going to return now or last executed. We still need to actually apply if. In other words, what we're going to get out of this is returns updated or previous timestamp, where the updated one is going to imply that we should run the function now, and the previous timestamp implies that we should know of.
There's either been a swap or there hasn't been a swap. If there's been a swap, that means
exactly.
Let's execute.
Exactly. And now this is actually a nice segue into another utility that was added into Clojure recently, which was nice, which is going to be useful over here, which is we want to swap in these values, but what we would actually like to get out of this as a return value is just this. We just want to know, was the thing elapsed or not? If we do this, let's say I just call this swap return, right? We effectively want to have this logic now. We want to say if val was swapped, right? We want to have something like this. If the val was swapped, then we want to do this branch here, result, which we don't need to do in a thing like that anymore. Otherwise, we want to do nil. So effectively, from a structural perspective, this is what we're kind of hoping for. We want to somehow check, was the value actually swapped or was last executed changed? I guess we can call it that way. If last executed was actually changed, then we're going to do this. The last executed was not changed, then we're just going to no op, which again, we could change to something like this. This is atomically updating the value of last executed, and it's using the correct logic. And we would now like to be able to say, if that last executed actually changed, then run the function, otherwise don't run the function.
I suppose we just need to figure out how to get that last executed changed out.
Exactly. That's now the remaining problem. How do we get this last executed changed out? So there's a couple different ways of doing this. One way that I tend to use is actually something in Encore, one of the libraries that I have that allows you to actually make a distinction between the return value and the new value. So Encore has something called swapped. Oh, Encore, I'll just show you how this works quickly. So Encore. So Encore would actually allow you to do something like this, where you say the new value, it makes a distinction between the new value and the return value. So you would say the new value is now, the return value is true, and then something like this, the new value is last executed, and the return value is false. And then this would actually just straight away be changed. Something like that. So that's a feature in Encore. But instead of using that, let's try use Clojure built-in stuff. And I believe that there is something in Clojure, it's one of the more recent ones that should allow this, that should be useful. We can use something, a function called swapped vals, which works exactly the same as swap, except that it's returning both the new and old value. In other words, I'm going to say it's old and new. And instead of calling swap, we're going to call swap vals.
Okay, so you're destructuring the return value there, where you get the old value. We expect if it executes, the old value would be last executed and the new value would be now. Exactly.
So now we have old executed and new executed, and changed is equal to this. So basically, it's going to return the old state and the new state, and we're going to check, are they equal? If they're equal, that means that there was a no-op. If they're not equal, that means that we actually changed it. So we have when changed, not equal, old executed, new executed, when changed, we have something like that. And let me try evaluate this and check that we haven't got any typos. It looks okay. Let's try run this at the REPL and just see that it appears to work. So we're doing a wrapper. We're saying minimum elapsed time is 100 milliseconds. We're wrapping the say hi function. We're calling this 3 times. Our hope and expectation.
It's going to execute once. The WF1 should execute, and WF2 and WF3 should fail. Well, should return null.
And that hopefully over here is the behavior that we're seeing. So it's printing once and it's returning once. And that's also the behavior that we saw the first time when we naively tested this function. But the difference here is that this one will actually ensure f will never be called more than once, even if you're calling for multiple threads.
Now we have atomicity, and we can put that in our docstring. And that means guaranteed behavior, where we won't ever revert to the old way, which didn't have atomicity.
So how about this? So I like that you mentioned the docstring. It's a good opportunity now to sort of reflect on what we've done and check again, what is it that we're actually promising? First call returns. So how about this? I'm just gonna bulk take this whole docstring. And what's the difference between the wrap once and wrap once in a while? Returns a function that wraps given function f, so that first call returns subsequent calls return nil. So the difference is it's no longer about the first or subsequent calls, right? So if f hasn't been called in bigger or equal to msec period, call returns okay, apply f args. Otherwise, I don't know if I would do it this way anymore. I think I would rather do it this way. Again, this is something that normally we would take some time to actually try and phrase nicely. If f hasn't been called in call returns otherwise, call returns nil without executing f. And you'll note something, which is our original rep once docstring didn't actually mention anything about multi-threading. And our new one so far does not mention anything about multi-threading. So a question for you is, should we mention something about multi-threading in the docstring?
So if the atomicity is something that you want to keep around, then you should mention it because it's something that will stick. If it's something that could change or may change, then just leave it out. It's safer to leave it out, but put it in if you want people to use it in a thread-safe environment.
So that's exactly right. So basically you would put it in if and only if you're intending to make the promise that that is the behavior. Now, the thing is, in this particular case, I might argue that this is the kind of thing that maybe you would not document, because I would probably assert that the thread-safe behavior is a fair thing to assume out the box. Because the fact that we're not saying f should not have side effects or f may be called multiple times or something like that, basically the question is if a reasonable user is going to read this docstring, what is their assumption going to be about concurrency? Is their assumption going to be that they need to be careful about f maybe in a multi-threaded, or calling this wrapper in a multi-threaded environment or not? I might argue that a reasonable developer who reads this docstring might presume fairly that this should be thread safe if it's not drawing any other attention to it. But other people might disagree with that. And certainly it doesn't hurt. I mean, it wouldn't hurt strongly to just make it clear in case you sort of are on the fence about it a little bit. So we can say, all right, over here something, wrapper is thread safe.
Don't stress.
Don't stress. Let's go with that. What I might realistically propose is actually specifying what do we mean by thread safe, because thread safety is a fairly wide or broad concept that might mean different things. In this case, I would probably try to emphasize precisely what it is that we mean by that, which is f will never be called more than once in a given period.
I suppose then you could take a wrapper is thread safe away, and you could just keep this as one of those points.
Yeah, something like that. So these are not good examples of docstrings because we're writing them quickly, and at least my relationship with docstrings is the kind of thing I write it, I read it out loud. It takes me a while. It would take me a while to come up with a nice, clear description, but something approximately like this. The important thing to reflect on at the moment, I think, is what is it that we're planning to document? We can probably improve the documentation and make it clearer, but the question of what should fall under documentation, at least I think, is an interesting question for this point in the process. So f will never be called more than once in a given msec, even if the wrapper is called from multiple threads, something like that, all threads. And technically, we could make that same promise for the wrap ones. So we could do the same thing over there. For folks that might be curious to dig a little bit more into this later on, I would suggest, again, maybe checking the code on Clojure core swap, looking at stuff like the swap vals API, playing with it a little bit, playing with the reset, trying to create some examples of your own where you deliberately try to cause race condition, right? Using a deref and then a reset. Try to cause problems where you actually have, test cases which fail in a multi-threaded environment. See what that looks like, and then try rewrite it yourself using swap or swap vals or even just a loop recur and compare set. Try do that stuff by hand so that you start getting a firmer grasp of what's actually going on. There's a lot of interesting stuff that you can learn from trying to produce problems that things like the STM and the Atomicity API and things like that are meant to address, so that you can actually see what do the problems look like when you have them, so that you can also develop that sort of spider sense that when you see a reset or you see a lone deref and then some additionals based on the value of that deref, it makes you uncomfortable because you're thinking, hold on, I'm derefing this value and then I'm making a decision based on the value, but time may have elapsed between here or there, or another thread may be executing in the background. And for people who are potentially working with multi-threaded code, that can be an interesting domain to sort of explore a little bit and get your hands dirty with.
Thanks, Peter. That was super cool. It was super interesting to go through. Interesting fact was Peter actually got me into Clojure, so that's a cool thing. And you'll only figure that out if you watch till the end of the video. So
I suspect
Peter.
no one's watched all this way. I've bored them senseless with
Well,
all sorts of details that no one cares about.
I would have watched all this way.
But you're crazy like me. I don't think we're representative of normal sane people. Thank you. Bye bye.